All right. Okay, I wrote again everything here, so the final results that we obtain, because you need to, keep them dear to you, because are sort of the standard quantity that are treated in cosmology. So we have the Friedman equations that are the solutions for Einstein field equations that deals and that tells you what is the dynamic of the universe, how A is changing as a function of time, given the energy density components that are filling the universe, radiation, matter, the cosmological constant, and whatever you want to fill the universe with. Then we define the critical density, which is the density for which the universe is flat. We introduce the omegas, which are the density contrasts, which are nothing but the ratio of the density with respect to the critical density, okay? So you see when rho is equal to rho critical, omega is equal to 1. What does it mean? That when the density of the universe is the critical one, omega is 1. The universe is flat, and we have seen in this other condition, right? By imposing k equal to 0, means omega k is equal to 0, we have this expression, this disappears, and we have omega equal to 1. And we obtain that by dividing by h squared the expression number 2 between the two Friedman equations. Okay, bottom line, we introduce this quantity, and as I promised, we are going to plug it into there, okay? So we plug it into the Friedman equation number 1. And before doing that, to have even a further splitting, since we know the explicit expression for the time evolution with respect to A, the evolution of those quantities with respect to A for radiation, matter, and cosmological constant and everything, remember, we use the adiabatic condition to do that, we can have an explicit expression for h to the power of 2, okay? H to the power of 2 is equal to what? 8 pi g over 3. This is just the constant. And then we can just plug in rho m, rho r, and the rest for all of them, okay? So we have rho r radiation, a to the power of minus 3, 7, 5, 4. Exactly. Remember, the universe is expanding. We have a volume dilution of the photon, so the number density is decreasing with the power of 3 with respect to A. So it's a volume dilution. The volume is growing. And another factor of A to the power of minus 1, because the photon frequency is stretched, sort of, and therefore their energy is going down, okay? So this gives you a total contribution of A to the power of minus 4. Then we have matter. So we fixed a constant. So these two rhos are the density of radiation and matter today. Okay, that's what we measure today, sets the normalization. And then we have the evolution with respect to A, which is A to the power of A to the power of minus 3, exactly. Number of particles, we assume it to be conserved, and as the expansion grows, it just goes through the volume A to the power of minus 3. And then we just have the other contributions. You can close it. Then we have minus k minus k to the A to the power of 3, so A to the power of minus 3. And then we have a minus lambda over 3. Okay? If we want, we can get rid of this guy and bring it into here. So what are we going to have here? Let's do that, which is a bit cleaner. Plus rho cosmological constant, so rho lambda. Then we have our minus k A to the power of minus 2. Okay? Just adiabatic condition. So that's just the rho of A coming from the adiabatic condition. Now we can use the definition of the omegas, and we can write this expression as h naught to the power of 2 times omega radiation times 0, a to the power minus 4, plus omega matter at time 0 for today, power of minus 3, minus omega k0, a to the power of minus 2, plus omega of the cosmological constant, which is just a constant. Okay? I just used this definition. You see? I have rho k, 3, h to the power of 2, 8 pi g. 8 pi g, 3. Okay? So I just divided all these quantities and multiply times the cosmological constant. I obtain all the omegas. This omega is just by definition, okay? Just a constant. So you see the 3 types of evolutions for radiation, matter, and the curvature, plus the cosmological constant, which is a constant, of course. Okay? Okay. And several times you write, you can see this expression written like that. Okay? Where E of A is what is within the parentheses. Sometimes you see them expressed like that. So what's the meaning of all of these guys? So H naught is one of the key importance of the cosmological parameters that you can read all here. Okay, so this expression, these are all the parameters that defines the dynamic of our universe. Omega 0 sets the normalization and tells you what is the expansion of the universe ratio today. That's why there is a 0. So whenever you see a whatever 0, this means today. Okay? Today, 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 and this is the dependencies that follows. So that's called the Hubble constant. And the units of the Hubble constant, as I said, is the expansion rate, so it's kilometers per second per megaparsec to the power minus 1. Okay, so it's kilometer is a length, this is a length to the power of minus 1, so these are two lengths that goes away, and s that are seconds, so that's the time rate, tells you that the units are s to the minus 1. So it's the inverse of a time. So you see this is a velocity. And this is a typical scale that is used in astronomy. These are megaparsec. So a parsec is the distance for which the angular diameter distance, so the separation of an object, changed by 1 arcseconds. Okay? So what does it mean? The parsec. Parsec, let's write it here, otherwise it's on the way later. Parsec. It means the distance that that we have once we have a separation of 1 arcsecond. Arcsecond. Okay, that's this angle, and the distance is called parsec. Is 1 parsec. So is a measure through parallax. That's the way. That's what you use when you open and close the eyes, right? You always played as a kid like that. You know? You open and close one eye, and you see the two eyes kind of moving like that, right? This is a measure of distance. That's why we can play basketball, soccer, and all of that. Otherwise, how do we know where to kick, how strong to kick? Okay? Anyway, that's the typical separation. So what's the meaning when we use all these? So it's a time rate, okay, seconds to the power minus 1. Or you can thinking at what is the change of the velocity of the expansion, every megaparsec. Okay? Every megaparsec goes away, the expansion is faster. That tells you that. Now it's called Hubble expansion, because if we don't use all of this expression, you know, we just stop at first order, we have the so-called Hubble law, where we have a distance that can be measured as c over h naught times the redshift. And the redshift I'm going to introduce later, but I just anticipated now, okay? So this is, again, another way of measuring distances that's related to A. We are going to see that. This is the Hubble law, which works only for very small distances, okay? So it's sort of this expression, but only at very low distances. Having this guy, since it's a unit of s to the power of -1, we can define the Hubble time th, which is equal to h naught minus 1. Just the inverse of h naught. And for our universe, given the measurements at end, is 13.9 gigayears. So 13.9 billions of gigayears, okay? That's called the Hubble time. Then we have another quantity that is called the Hubble radius. And again, it's just a definition, and it's just RH, and we define it as c h naught minus 1, right? This has times of unit, speed of light, that for our universe is 4.2 gigaparsecs. These are typical scales characterizing the universe, okay? Now, take care, because these quantities are instant quantities. They are not integral quantities, as I'm going to show you now. Because if you measure a distance, okay, the units are all fine. I mean, this is h to the -1, so these are seconds times a velocity is a length, right? This guy is unit of seconds to the -1, seconds to the -1 to the power of -1. These are seconds, so years is a h. Okay, but these are just typical time scales that we set. And when we deal with distances in cosmology, or times in cosmology, we need to account for the fact that as we are speaking, the universe is expanding, right? Because if I start to take a measure between here and that, I can use light or any other means, and as I do that, the universe is expanding. So I need to account for the evolution of the time as that occurred in doing this measurement. I'm going to give you the mathematical expression, is much clearer than words. But before arriving at that, we can speak about this Z guy, the redshift, okay? Because what the construction that we did is beautiful, it's fantastic. We have our dynamical value that is given by A, and now I tell you measure A. Use a stick, length, how can I do it? Therefore, we need to link A to something which is observable, and that's the redshift. Redshift. So we are linking A to a new quantity that we call Z. And of course, we can do the step backward. From redshift, we can recover A. To do that, we just linking our something to we want to link something that is observable. For example, through spectroscopic observations, right? Because what we said, that we have galaxies, for example, that are expanding. And they're expanding how? Following the metric, right? There are proper motions, but let's forget about that. On large case, they are expanding, and the expansion is driven by the expansion, by the expansion A. Okay? Therefore, we can think at the galaxies in a naive way, if you wish, that they are going away from us. And the speed at which they go away from us depends from their velocity. We can read it from here or in a simplistic way from here. The further we go, the faster the galaxies go. And this is clear from the fingers that I showed you a few lectures back. Remember, the universe is expanding isotropically and homogeneously, and each point is going away from one from each other. So if I take this as a reference, look, you see that the other finger has to go faster because the velocity sum up this velocity, this other velocity, and this other velocity. Okay? Therefore, the further we go, the faster the galaxies are expanding. That's sort of a picture to have in mind. But formally is captured by this expression. Good. If this is true, if this is the case, then we can understand the velocity of expansion. You know that there is a relationship between the velocity of recession of the galaxies with the A factor, the constant, the expansion factor. And if we have our velocities of the galaxies which have their own velocities, and if they are emitting some radiation, I can use a spectrograph to measure the frequency emitted by those objects, by those sources. And you know that if an object is going further away from you, it means that it's redshifted. It gets redder. If it gets closer to you, it gets blue shifted. It gets bluer. There is a shift in the frequencies. Just think in terms of Doppler effect. Okay? Therefore, if a galaxy is going away slowly, it means that it doesn't have a lot of redshift. So it's redshifted by a bit. A galaxy that is further away is expanding with a faster speed of recession, and therefore is going to be more redshifted. Okay? Therefore, less red, more red. It means close and slow. Faster, more red means faster and further away. Okay? And therefore, we can use something that is observable, which is the frequency that is emitted by an object. So that's the original frequency. That's the one we measure. And it's just normalized with respect to lambda. That's the definition. That's the definition of redshift. So it's a quantity based on frequencies of some source that we are observing. And it just looks at the percentage variation of the frequency with respect to the original one. With original one, I mean the emission at rest, the radiation that is emitted at rest. And of course, I can write it as well like that, -1, but is a ratio of wavelength that I can relate it to frequencies. And frequencies are the reverse of the wavelength, right? Because the frequency depends on 1 over lambda, as well as lambda depends on 1 over the frequency. -1, we don't touch it, and it remains there. Now what we have? Oh, we have 2 frequencies here. So a frequency is what? Is a time rate. Okay? Therefore, we can call it, this guy, dt over dt, where the one at rest is the one above, because the units of frequencies is 1 over time. So if we take the unit of nu, are seconds to the power of -1. Therefore, where you have the not here, it appears up here, and vice versa. Okay? And of course, the -1, we didn't touch him from there. Nice! But now we have a relationship between redshift and the time clock at the time of emission and the one that we can observe. How can we link it to A? Through the metric. We are using the metric. Therefore, we have our ds to the power of 2 equal to 0, because we are talking about radiation, or photons. For photons, and the metric in general as our minus c squared times dt to the power of 2, plus we have a to the power of 2 as a function of time, and then all the rest for the space components. Yeah?
Lambda 0 is the wavelength at emission, right?
Lambda 0 is the wavelength at emission time. Ah, no, sorry, the way around. At observation time. Sorry, you're right. Sorry. O, let's write it. O equal observer. Yeah, so it's always positive in this sense. Okay? It will be negative, it will mean that there is an increase in frequency, it's coming closer. Okay, good. So we have everything. We have this spatial interval. And the relevant part, because we can always set a frame in which we are at rest, this guy is going to sleep, right? We can set it to 0. So you see we have a ratio, we have a clicking time for the time. So the expansion, we can set this guy as a fixed length because we can choose any arbitrary length, and we can call it R. Okay? If we have if we are in another frame, so this might be the frame of the emission, we can have the same the frame at our so the 4 interval in our frame, the t0 to the power of 2 plus etc. a square a t, and then we can choose the same length. Now what we can do? Well, that's at t0. Where is the 0? I put it here, so that's here, t0. Nice. But now we have, you see, an expression that relates the t to a, because I can just bring the t on one side, and I have an expression for a. That's equal to 0. I have the t equal to what we have on the other side. So I can just get this t0, the t0, and plug it here. If we do that, what we obtain is nothing but a at t0 with respect to a at t minus 1. We have our relationship between z and between a. Of course, a t0 is today. Okay? And by definition, we call it 1. We set it equal to 1. 1 over a t minus 1. And we set by definition. If we do that, let's just write the expression of a of t as a function of redshift. So you see, observable quantity through spectroscopy, for example. So I can measure it, I can measure it, I can measure A. A is a direct observable. I can directly constrain it with observations. That's why we can always use as a time units, just to see at which stage of the universe we are in its history, A time or redshift. You can always transform one into the other. This is always an expression. Now I gave you, and again, if we want to go back to cosmology and to what I said about general relativity in general, is the fact that many times here it's, we are always referring to the velocity of galaxies. The galaxies are going further away, Doppler effect, and blah, 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 all of that. That's what I said. That's the typical picture that we have in mind. But at a deeper level, and that's also something that you have in the exercises, this is coming about by the fact that we have a time evolution of the metric. Okay, the metric is evolving as a time dependency. Okay, that's important because it has a dependency on A that is depending on time, right? The time dependency is making the metric evolve. We do not have killing vectors, time killing vectors. We don't have energy conservation. Strictly speaking, we don't have energy conservation. And again, to see that, we can write our energy conservation law. You know that this guy must be this equation must be satisfied. But if we look at this expression, we know that it contains the standard derivative of the energy momentum tensor plus the contribution that comes from the Christoffel symbol. Okay, mu gamma, if we want to look for the energy conservation, we go for 0, for the 0 component. And then make a mess, mu T gamma 0. And then the other one, again, 0 component, mu gamma T mu gamma. Yes. And that must be equal to 0. And you see that with respect to special relativity, we have this additional term. That's sort of too much. We have the mu T mu nu equal to 0. No, it's not true. That's the strict energy conservation as we intended in special relativity. Energy conservation strict. We have these additional terms that are coming from the curvature of space-time. This breaks this picture. Okay? That's why we say that is not conserved. To have, I was speaking earlier with one of you, you can think in that term as the energy that goes in the gravitational potential. Okay? The energy momentum tensor is not well for the energy of gravity itself is not well defined in general relativity. Okay? But you can picture as if there is a gravitational potential that is storing energy, as in Newtonian gravity. Okay? It would be the analogous. It would be sort of captured by these guys. Now I'm stretching a little bit the mathematics. Okay? But just to tell you, my message is the deeper understanding of the redshift is not by they're moving away, but the energy is not conserved in this sense in general relativity. That's why photons are. That's why photons are getting redder and redder as the universe expands. Good. Having said that, we can move to the last bit of today's lecture. Oh, actually not, because the time is up. So let's make a small recap about this short session now. So we defined basically this omega critical, and we introduced this definition in our Friedman equation, such that we can write it in this way, okay? So look at this expression very carefully, because that's the one that is reoccurring every time in every paper that regards cosmology, this one. Then we discussed the fact that the Hubble constant is as unit of times to the -1 and can be used to define a typical time scale for the universe. As well, you can write it in this way, and it tells you what is the speed of recession of galaxies for each step in distances. By looking at the Hubble law, so you will see this h, this tells you that galaxies are receding with a further velocity the further we go from us. Then we looked for something to make to link our fully theoretical prescription that incorporates this expansion function to something that we can measure and observe, and that would be redshift. Okay? So our redshift is just defined in this way, as we would do for standard Doppler effect. And by looking at the time clock changing, we can link it to our expansion factor through the 4 interval. Okay? So observational definition of redshift, as you would do with the Doppler effect. So I'm stressing that as you would do with the Doppler effect, observation quantity, and we link it to time rates. Time rates is linked to the metric. You see, I'm not talking about velocities. I'm talking about the fact that the metric has a time evolution. Okay? Do you see that? Through the 4 interval. That's the thing. The metric is changing. Metric is changing, gives you a Doppler effect. And we have our expression in which we have the relationship between A and something we can observe. And again, keep in mind that A depends on T, that depends on redshift. With root is a very simple expression. Then we are going to see also A of T explicit. And we can use A, T, or Z to define the time at which we want to define our universe. And that's it for this. Next time, we are going to discuss distances. And we are going to see how it's not that easy to, or let's say it's not immediate to define distances in cosmology, because we are living in a dynamical system. The universe is expanding as we speak. Therefore, if I want to measure something from E and there, I need an integral over time that is going to come into place. Plus, we are going to learn that there are different ways of defining distances, because we will see that there are luminosity distances. So distances, we have a specific definition of distances. Once we measure, we do that by measuring fluxes, for example, supernovae. Or we have a different way of measuring distances where we measure angles in the sky, as we are doing here. Okay? And in that case, we speak about angular diameter distances. After we learn how to measure distance and define distances in cosmology, it is our living, expanding universe, dynamical universe, we are going to define 2-3 definitions of horizons that are important to know when objects are causally connected in our universe. That's important if we want to study microscopic processes that take place within our universe. For example, thermalization. Can this region and this region thermalize? Well, it depends. It depends if they are within the same Hubble horizon. Otherwise, they don't. Okay? And this is going to be crucial to understand the thermal properties of our universe and why it looks as it does. Good. So we can stop here. I'll see you next time. Thank you very much.